example of it where we are looking at data that has a particular confounding factor in it, which is a problem because of the way that it's a good random sample. It's not like our problem, this problem where we didn't get a good random sample, but this problem is just part of the nature of the population, which introduces a confounding factor. Okay, and what I'm going to do, this is based on something that the New York City Department of Health publishes every year, called the morbidity and mortality report, or vital statistics. New York City vital statistics. Who knows what vital or vita means? In Latin, vita, life, right? Life statistics. Okay, so, New York City vital statistics. Here we go. And you'll see that they have a number of them here. Here's our annual report for 2015, and there's an archive of vital statistics annual reports going back to 1961. I'm going to click on this one, and if you look at this, the opening page is a summary of the crude mortality rates in New York. When I say crude, it's not adjusted for anything. It's just the number of people per thousand population that died that year in New York City. And if you look, back in these days, back in the start of 1800, they started keeping records. Periods when 50 people per thousand died in New York City. That includes a fairly young population, right? So why did that happen then? Well, we had a cholera epidemic, another cholera epidemic, a smallpox epidemic, so on and so forth. Here, the most recent big spike is over here in 1918, the pandemic flu. Of course, every year now we're worried about a pandemic flu coming back and getting another big spike in the mortality rate in New York City. Okay, if you look down here, something for what is today? Today's September 11th, right? 9/11, right? If you look down here, they make an inset here because if you look at the chart, it's very smooth going down over time, but it's very smooth. They put this inset in here to let you know that they did not include the mortality from the World Trade Center in 2011. They probably have a reason for that because it doesn't fit in with their tracking of disease rather than crime and stuff like that, but basically criminal actions and stuff. So this is what it would have looked. There would have been a bump down here like that if they had included those 3,000 or 3,500 deaths in 2011. But if you go through this now, it has many tables that give you information about the life expectancy in different areas of the city, about mortality rates from different diseases, the actual literal counts of the number of deaths. For instance, leading causes of death in New York City, top 10 leading causes of death ranked by age and gender. So for instance, if I go here to 15 to 24 years, the leading cause of death was assault or homicide for 15 to 24 years old during that period of time during that year. Okay, and how many of those? 101 of those were males, and 7 of them were females. So we have some interesting information here. I'm going to focus on one: diseases of the heart, or cardiovascular disease. For that age range, there were 15 deaths in all of New York City during that period. If I go spin up to 45 to 55, now let's see. Whereas diseases of the heart now with the number 2, and there were 827, and so on and so forth. And of those 827, so many were male, so many were female. I'm not looking at that right now, but I can literally put together a summary by age range of how many people died from cardiovascular disease in New York City. And we have on Blackboard, we actually have a file like that. Okay, I'm going to open that up now. Let me find it. Okay, this is not from 2015, it's from an older set of data. Oops, that's an older one. That's a different one. There we go. Let me blow this up a little bit so we can see a little bit better. Okay. Okay, so here we go. Here's my table here. From 24 to 44, there were 146 deaths from cardiovascular disease. There was also information about the population in that age range. Okay, females had 144 deaths, males had 277 deaths. Population of females at that time was, in that age range, was 1,356,000, and so on. So I'm going to calculate an age. So first of all, before I do anything, I'm going to add up all the deaths. There were 12,000 females that died during that year from cardiovascular disease out of 2,854,000. So I'm going to click into this box. I'm putting an equal sign in there. And I'm going to say, well, the rate of death of cardiovascular disease was the number of deaths divided by the population. Now that's going to come back a really awkward fraction, like 0.019, whatever, right? It's going to be hard to interpret. So if I multiply by 100, like if I got 0.25, I multiply it by 100, it becomes percent, 25%. I'm going to multiply by 100,000. So it's a number of deaths per 100,000. I'm going to put parentheses around here first, and I'm going to multiply by 100,000. Okay, 442 women per 100,000 women died from cardiovascular disease in New York City. I'm going to do the same thing for males. That's the number of males that died, smaller population, lower number, but smaller population. And I'm going to put the parentheses around here again, and I'm going to multiply by 100,000. 413. The rate of mortality from cardiovascular disease in New York City was lower for men than for women. Does that make sense? It's counterintuitive, right? You would think it'd be the other way around, right? Well, gee, that's why is that happening? I mean, what is the, why did they get such an unusual result here? Well, first of all, notice, what did I call it here? I called it the crude mortality rate, just the simplest calculation of mortality. Number of people died over the number of people that were living in New York City at that time, right? Well, how about this? How many 80-year-old men do you know versus how many 80-year-old women? Women tend to live longer than men. New York City has an older female population than they have a male population. So since there are so many, and as you get older, the rates of death by cardiovascular disease increase. The problem we have here is not that women are really dying at a higher rate than men are from cardiovascular disease, but their population is older. So by nature, they're going to have more of them are going to die from cardiovascular disease. So to really understand this data, we now have to adjust it. We have to standardize this data and take out that confounding factor of the differences in the distribution of population by age. Okay, so how are we going to do that? Well, first thing we're going to do is we're going to calculate age-specific death rates for each of these groups. Okay, so this is going to be equal to 146 divided by the population. Okay, that's the rate at which women are dying in that age group. I'm going to copy it down and do it for all the other age groups. Right? You saw me click in there and drag. I could say copy the whole thing, and it would do the same calculation each next to each other. I'm doing this very quickly because I want to just get through this so you guys can see me do it once. 277 divided by the population in that age group. I'm going to copy that calculation down. Okay, so that's the rate. Notice the rate in the oldest age group, the rate is much higher than this in the youngest age group for the rate of death from cardiovascular disease. In this older age group, it's literally, say 85 plus, it's literally almost 8 per 100 people that die from cardiovascular disease in that age group, plus 85 plus. Okay, and if you click in here, you'll notice that it actually copied the formula down, F10 over E10. This next one's going to be F11 over E11, and so on and so forth. Just by grabbing and recording, copy it down. The other option I would have had, just highlight the whole thing, go up to Edit, and say Fill Down. Okay, and it copies the formula down for the side-by-side columns. Okay, so now I am going to, now the problem here is that this is my female population. Notice how many people are over 85 in my female population. How many are over are 65 to 84 compared to the males in my population that are in my age range. different distribution for these two populations. So now what I really need to do is take these age-specific death rates and I need to apply them to the same population instead of two different populations. I can make a population up and say there's just 100,000, there's 1,000,000 people in each age group, right? But that's kind of like cheating a little bit, right? Doesn't make sense. How about if we relate it to something that may make some more sense? Why don't I just apply it to if the total population of New York City, if we applied it to the total population of New York City, female rate, male rate, and compare those rates, maybe we'll see if there's a difference then. So here, I've got, all this is here now is the total population, which is just the males and females added together for that age range. Okay, so I'm going to take all of these numbers, the age-specific death rate here, I'm going to say copy. I'm going to go down here, and I'm going to paste them in here. I'm going to say paste special, and I'm just going to paste in the values, not the formulas. Makes it easy for me because then I don't have to worry about, relating these cell numbers. So I'm going to do the same thing for the male specific death rates. I'm going to say copy, and I'm going to say paste. Paste special, and choose values. Okay, so now I'm going to use those rates to estimate how many deaths I would expect if this population, the same population, were dying at the rate that age-specific rates that females die at and the age-specific rates that males die at. So I'm going to do it for females first. Equals the population times the death rate. Okay, and I'm going to copy that down. And I'm going to add them all together. So how many deaths would we expect among females if this were all a female population? Turns out to be 19,552. I'm going to do the same thing for males. Males equals the population times the male death rate for that age group. And I'm going to copy that down. If I can grab it. Whenever I'm trying to get something done quick, you have these problems, right? Now I'm going to calculate the total number of deaths. I'm going to add these together. Okay, so now I'm going to calculate what my mortality rate is now for females and males. So I'm going to click in here. It's going to be equal to the number of women that would die that would die if they died at that rate. Over the population times 100,000. And the rate is 371. Let's do it for males. Equals males dying at their rate that they die at for different age groups, but now applied to an identical population instead of two different distributions. Okay, it's going to be equal to okay, going to be equal to the total number of male deaths we would expect divided by total population and times 100,000, and that rate is 511. So now we get the real comparison. Men die at a higher rate than females do. We've extracted that confounding variable age by standardizing this data on a single population with a single distribution, rather than with two different distributions. Where one was biased because there are a lot older people in that population compared to the other population. I'll post something else I'll post another copy of this, a different copy. I'll post this and the answers to it, but I'll also post another file, another Excel file that you guys can play with that compares deaths due to cancer in Alaska and in Florida. Okay, so what do you think? The problem is going to be the same problem, right? Except where's the older population now? It's in Florida, right, compared to Alaska. Okay, so the crude mortality rate is going to make it look like people are dropping like flies in Florida from cancer, because who knows